In the previous video, we spent a lot of time on a digression on Euler's theorem that we weren't able to talk about the next one, binomial series. But I do not regret it. Euler's theorem, this one, and the applications are so beautiful. Important, yes, but for higher level mathematics. But mainly they are beautiful, so that I don't mind sharing with you using rather significant amount of class time. Okay, let's now move on to class materials. Binomial series. We talked about the Taylor series theorem, and then some examples of Maclaurin series expansions are here. E to the x power, cosine function, sine function, and then the next example is binomial series, 1 plus x to the k power, where k can be arbitrary real number. If k is a positive integer, then this becomes a binomial theorem. And we do not have infinite sum, we have just finite sum, and it's running from just 0 to k, because if n exceeds k, then binomial kn will become 0. Well, here's the definition of this binomial kn. K factorial over here, k factorial over n factorial times k minus n factorial. And let me increase the font a little bit so that you can see things better. And this one makes sense when k is positive integer and n is also an integer between 0 and k. In that case, we have a combination k choose n. However, if we get out of that bound, then this highlighted expression does not make any sense. However, this one does. So we're going to use the latter expression as the definition of this binomial kn. In this case, if k is integer and n exceeds k, then, for example, n is k plus 1, then what do we get? This factor, k minus n plus 1, will become 0, so this entire expression will become 0. And the same thing is true when n exceeds k. For example, n is k plus 1 or k plus 2 and so on. One of those factors from here to there will be 0, and this entire thing will become 0. So we end up with, even if we stated this one as an infinite sum, we end up with a finite sum where n is moving from 0 to k only when k is a positive integer. For arbitrary k value, arbitrary real k value, we're going to get an infinite sum, and we have, well, this kind of series. It's an example of a Taylor series too. Let's see. Shall I go over to some example problems? Find the Maclaurin series expansion of the given function. Oh, this is really easy. All I have to do is to go to this form and then replace x by, copy it down, and then replace x by negative x over 2 here. And that's basically what we did here. How about the next theorem here? That's not as simple, but still it's again very easy. All I have to do is go to this expansion of cosine function, replace x by 2x, and then multiply x at the end. In short, this is what we want. Here we want to replace x by 2x. Consequently, this is what we did, and consequently we get this infinite sum and multiply by x, so we have x to the 2n plus 1 power. Third problem is a little bit more challenging, and this one is related to binomial series. And look at the binomial series theorem. We need 1 plus x to the k power. We have 2 here. So what we do? Well, let's go back to our bag of tricks that we used in the previous section. We have to divide by 2 and factor it out to change it. And this is a typical trick. We are using, well, we're using this result. We are using this one. And k value is 1/3, so 1/3 power. And we need 1 here, so what we do, as before, factor 2 out, and we have 1 plus x over 2. And factor 2 out completely, then we have 2 to the 1/3 power, or cubing root of 2. And then we have this binomial. We can apply binomial theorem, and we have binomial 1/3 choose in, and then multiplying 2 to the 1/3 power to each denominator, we get 2 to the n minus 1/3 power in denominator. Okay, that's enough. Is it really necessary to go one more step here? Kind of like this one. And k is gonna be 1/3, and then this is 1/3 minus 1, this 1/3 minus 2, 1/3 minus n plus 1, and so on and so forth. And then we have x to the nth power, 2 to the nth power minus 1/3 power. And okay, here's an alternative expression of the same thing. Again, please remember this trick. This one had better be 2, so factor 2 out, generate 1 plus x over 2, factor this one completely out, and then replace x by x over 2 in this Taylor series expansion of the binomial. This is very similar to the trick we use for log of 2 plus x, kind of like that. Oh, wait a minute, excuse me. As a matter of fact, excuse me, what I did here is incorrect. I just took 2 plus x to the 1/3 power, even though the problem was asked as 2 plus x squared here. So what I did here is this problem. And if you want to do 2 plus x squared as we have over here, then let me see, this has to be squared. So this has to be squared. That has to be squared. Oh, excuse me. This one has to be squared. So that has to be squared. And this is not x to the nth power, x to the 2nth power, otherwise no change. And this one has to be x to the 2nth power, otherwise no change. And then for the interval of convergence, we need x squared over 2 is between -1 and +1. In that case, a negative part does not do anything. X squared over 2 is less than 1, taking x squared. So taking we get x squared is less than 2. Taking square root of each side, we get negative square root of 2. And that's gonna be the full solution of this problem. Please forgive me of my mistake, but I was able to correct it on spot here, and this solution is now complete. This one is correct. And let us check this. This Mathematica command will generate, yes, 2 plus x to the 1/3 power. That's not what we wanted. What we want was x to the 2nth power over there, and that will be, that's what we want, 2 plus x squared to the 1/3 power. Okay. We went through 3 problems, one really trivial, just plugging into Maclaurin series expansion for exponential, and almost as trivial, plug in 2x to the Maclaurin series expansion for cosine and then multiply by x. And then this one was really worthy. Even without x squared, it was worthy. Here is the formula for binomial expansion. And then we had to do some manipulation, factor 2 out to force 1 plus something there, and replacing x by x squared over 2. And that generated all these. Factoring 2 out completely, we have to multiply 2 to the 1/3 power to each term. Okay, how much time do we have? Let's move on to some further examples. Oh, looks like these problems are ugly. We will have to calculate the derivatives repeatedly, find the Taylor series. Maybe 3 or 4 derivatives will do. And that's going to be really tedious. What did I do here? Yeah, I made the right decision. I decided it was so tedious that I just used Mathematica program to calculate the derivatives for how many terms? 10 terms, and then express those here. Okay, so it is tedious. Repeat is differentiation, easy but tedious. How about this problem? Again, it was so tedious that I decided to use Mathematica program to calculate the derivatives and then plug in C value. And this time I took n equal to 5 terms. How about this one? This time I did do some work. Oh, I see. This one really deserved our attention. Okay. Because we have a trinomial down here, it's not really as obvious that we use binomial series, binomial formula over here. So we may have to use repeated differentiation to calculate the power series expansion, but well, repeated differentiation, that's no fun. That's really time consuming. So let's move on to a little bit more clever method. This is -1/2 power, and complete the square here. This is x squared plus 6x plus 9 plus 4. So we have this complete square plus 4. Now we want 1 plus something for my binomial series. So factor 4 out, then 4 times this one. Well, let's put 1 plus over here instead of over there. Well, never mind. I did take that step in the next term, so let's do it here. So divide everything by 4, factoring those out. And then factoring 4 completely out, we have 4 to the -1/2 power. And inside here, 1 plus this complete square, and we have binomial. So binomial theorem applies here. Not binomial theorem, excuse me. Binomial expansion applies here. Binomial -1/2 n, and then this one to the 2nth power. And we have the final result here. How about some other problems? Well, we can use the series expansion for, looks like these are important, so let's do those in the next segment of the video.